Let me apologize in advance. I have to duck out either right before the end or right at the end of your talk. So I'm going to move to the back, and when you see me leave, it's not because of you. But I'm going to stay for as much as I can.
Good. Now I don't have to answer any questions. All right. Well, in that case, I'll say my thank yous now before you go. So, Dr. Calhoun, thank you very much for accommodating us for this time. Special thanks to Dr. Locke, too. Thank you to Ben for helping with any questions I had, to Luis, who's probably in the Alps somewhere enjoying himself, for really helping me with a lot of the stuff that I did. And thanks to the NSF and to Assist for funding it. And of course, thanks to Diana for doing all the behind the scenes work and helping out for everything. Thanks, Terry, for buying all this stuff for us, too. So I'm Todd Menadier. I teach engineering and entrepreneurship at Albemarle High School. And this research that I focused on was creating a targeted energy analysis for the feasibility and optimization of a larger scale wireless sensor node deployment. So what does that all mean? So we currently have large scale sensor nodes deployed all around us, and we use them on almost a daily basis, right? We use our apps on our phones to track what kind of traffic conditions we might have on our way to work. We use other things to figure out what the weather's like, and then we can also use it for a lot of other things that are much more specific, like how much water does this exact tomato plant in a greenhouse in California need at this exact moment. So we're using these sensors a lot more often, and as many of you know, we're trying to make these sensors become more reliable, some might even say more robust, and we use things to make them more efficient, and creating these sensor nodes is a means of kind of making a way to harness the sorry, let me just rewind it. So you take these sensor nodes and you actually have an energy harvesting capability employed on board. And when we look at that, we have a couple of options for what type of energy we could actually employ. So we look and we see that we could take a photovoltaic cell, we can use that to transform the energy from the sunlight into usable energy for our sensor node. And we might be able to get outside about 1,000 watts per square meter. Indoors, we can get anywhere from 1,500 microwatts per cubic centimeter. We could also use something like a piezo wafer, which is going to allow us to generate around 500 microwatts per cubic centimeter as well. So these are your options if you're designing this particular energy node to be placed out in the field somewhere. And so before you would actually go and place it out there, you would figure out, well, how much energy does my node actually use? So here's an example from research that other people have actually done, where they connected their sensor node to a DC power supply, and they figured out, well, in our first stage, when we have our sensors on, we're going to be drawing this much current. Then we have to take that information, we have to transmit it back somewhere for it to be used. And then we turn the sensors off, and then our processing unit that's on board of our node turns off as well. And then it goes to sleep until you decide for it to take another sample. So now you take your information that you gathered about your particular node, you now have all the powers from those 5 stages, you add those together, and then in some cases you have a supercapacitor on board. That's going to have some power loss as well. And you might have something that does some voltage regulation, so you're going to lose some power from that change in addition. So now you know how much power is necessary to operate this particular sensor node for whatever sampling rate you decided on. And then you go back and you look at that table that says, okay, you can get this much power from your photovoltaics or this much power from your piezos, and you say, all right, well, I'm going to use one or the other of these, right, based on the information that's provided in this very generic table. And then you go out into the field, you launch your deployment, and you put these sensor nodes in specific locations, and much like the work that Crystal did, where she actually went into a river in this case and took some time and effort to go to that location and place their generator in the water, you end up getting absolutely nothing, right? Because you focused your idea on this concept that that amount of power that was listed in some table somewhere was actually going to be available in the exact place where you're going to locate your sensor node. So my solution was to create a wireless sensor network in order to figure out if your wireless sensor network would actually make sense. So I created a way of figuring out how much lux, so we have a light meter right here, and how much vibration energy would be available at a particular site. And I did that by using these two circuits. So the one on the left is our receiver, and it's basically just an Arduino that would be connected to a computer somewhere. And it's outfitted with an X-speed transmitter, which is the blue part right there. And it has the shields that allows that transmitter to connect directly to the Arduino in a very simple manner. The one on the right is our wireless sensor node, so this will be placed in the field somewhere, powered by a 9-volt battery, because again, we're trying to figure out, is there enough energy to be harvested, so we don't really have to harvest energy at this point. And same thing, it's connected with our XP to the Arduino. So I collected the data, and here's what we got back. You'll see that on the accelerometer, you get this nice vibrational pattern going. So the object that I placed this on was the condenser unit of the residential HVAC system. And you'll see that you have a wavelength that occurs in approximately 10 seconds. So with a period of 10 seconds, you would expect a frequency of about 0.1 hertz. And when you run a Fourier transform, which is just a fancy way of saying, how do I calculate the actual frequencies of this data, you'll see that there's a peak at around 0.1 hertz. Okay, so our data is fairly consistent. Now, what does this actually mean for feasibility and what we can do with this? Well, this is a data sheet from a piezo generator company, and you'll see that the power output versus frequency is listed here. And as an example, the PPA 1011, which is a specific piezo generator from this particular company, can produce about 5.5 milliwatts at 20 hertz. Okay, so if we go back and look at the data that was collected from the accelerometer, you'll see that at 20 hertz we do have an actual peak. So there is a fundamental frequency based somewhere in that vibration that we could utilize. However, the amplitude of that is only 0.1. The amplitude here represents the amount of G's that are present. And up here, you have 0.5 G's. So we're nowhere near the amplitude necessary in order to create this amount of power using this particular piezo generator. So essentially, you could feasibly use this data to figure out which piezo generator you could use. In this case, none of them would actually be feasible. But it's nice to know that before you purchase this, go out, set it up a node, and place it in a particular location. With the light data, I placed the sensor in a location that would become shaded after a certain time. So you'll see that after about 10 minutes of time, the light that's available drops significantly. And that was done on purpose because, again, it shows that if you were to just base your design of your energy harvester off of this generic data set, and that data set said something like, hey, you're going to have 2,600 milliwatts of power throughout the entire course of the day, and then your area gets shaded, you lost that power, and now your capacitor and the rest of your circuit may not be optimized to reliably send the data back to the network that you want to send it to. So you'll see the graph's exactly the same, except here, converted that lux to watts per square meter, so now we know, okay, there's this much light. How much energy does that translate into? And then taking this and using this as a means to optimize your particular sensor node by converting it to how much power would be available for an exact type of solar cell. So here, again, collected from a data sheet on the solar cell, you get the area based on the length and width. And you can figure out, based on a 15% efficiency rating in this case, that you're going to get this many milliwatts of power. Again, the shading drops off, and you see how much you have for the remainder of the day. This value, this baseline value, would be more useful for you than a value, up at a higher range somewhere, because now you can size your capacitor that you're going to place as your energy storage according to the actual amount of sunlight and the actual amount of power that's going to be available and produced by your solar cell. So there are a few things that I would do if I had a little more time and if I can go forward with this. The first would be to find a better means of attaching the actual accelerometer in particular to something that's vibrating. In this case, it was kind of tricky for me to do on an HVAC system in my house. with all the wires that are connected to the actual sensor. And you can tell there was a lot of noise in that signal that I got as a means of it. And also just orienting it better so that way the x-axis, that's the accelerometer is measuring, is actually ranged between 0 and plus or minus -1. I would obviously collect data from more places and possibly more equipment, hopefully something that I could utilize in the future. I know there's work being done here on campus where you want to go out and test the steam units that are here, so maybe some of those exact motors would be an ideal place. And then I realized after purchasing the lux meter and actually coming up with this design that lux is not easily converted into watts per square meter, so figuring out a way to solve that would be, probably a better approach would be to take the actual solar panel, create a current voltage curve, and then utilize those values instead. So how would I bring this back to the classroom? It's nice because I teach engineering, and there's a lot of engineering-related topics that I learned here. So we would definitely focus a lot on how to use Arduinos in general, which is already part of the curriculum, and talk about how things like wireless sensor nodes are used in everyday areas like the Internet of Things. We do a couple demonstrations, so we have a lot of sensors available at the school, so I could show them how to actually set those up and just run an Arduino, not wirelessly. Also show them and demonstrate the actual system that I created. And then kind of set them free to explore. Just here are some sensors, here are some Arduinos, go out and see what you can do, and come back with that information. And then we'll talk about what you learned from it, how you can take that forward. And then all the work that I do in the engineering space at Albemarle is based around challenges. So a lot of it is kind of self-guided challenges. So I'd say, your only constraints are you have to use the Arduino and sensors that are adaptable to an Arduino because that's what we have. Other than that, I would set them free and say, here you go. So here's the design challenge. It's very generic, very basic. They would follow the engineering design process, going around in a cyclical pattern, following all the steps that they're very accustomed to by now. And I would tell them, just go ahead, identify some sort of problem that exists in our classroom, in the school, in the community, get some sensors, collect the data, wirelessly transmit that data, and then use that information to create some sort of a solution that you can then implement in the school or just present to the public. Okay, thank you very much. And are there any questions?